Good afternoon. Am I audible, everyone? So, what did we discuss in our last lecture? What topics we discussed? You don't remember? Maybe I should ask this question first and then set my projector. At least before that, you'll scroll down the pages, right? When you're not writing notes, just see, no? What is this? What topic? So, what is temporal difference method? We were discussing the model free setting, right? Where we do not know the dynamics of the MDP. So, when we do not know the dynamics of the MDP, how do we find V pi for a given pi, right? So one algorithm was Monte Carlo algorithm. In Monte Carlo algorithm, what we were doing is we were just acting according to pi and interacting with the environment. And if you want to find V pi of s for a given state, you just start from the state s and run one whole episode, like interact for one whole episode. You will get one sample for V pi of s. You get multiple such samples and then take the average of them. Then you'll get some estimate of V pi of s. So that was the model Monte Carlo method. And then we looked at what is called the temporal difference method. So in this, we were just using in this we were using the Bellman expectation equation, which is this. We were using the Bellman expectation equation, which is this equation. And what we were just looking at what to substitute for each value in this. Like instead of R pi of s, we are substituting one sample for that, which is RT plus 1. And then we had expected V pi given s, V pi of st plus 1 given st equal to s. So instead of that, we just substituted V old of st plus 1. So we had this general template, which is V new equal to V old plus alpha into some estimate, your new estimate minus your old estimate, right? So this is a general template which we have been following, and in this part where we are substituting the sample for the new estimate, we just substitute RT plus 1 plus the immediate reward plus the estimate of the remaining return. We just substitute the old estimate which we have. And we looked at few differences between the Monte Carlo method and this method. Like it was like the Monte Carlo method was offline algorithm. So you have to wait for an episode to end to update your estimates. In TD methods, you are able to update online. After every step of interaction with the environment, you can update your thing. And there are a few other differences which we have seen. And we also looked at what kind of values these estimates converge to, right? We looked at some simple example like this, and we have seen that there could be two different answers for this problem intuitively. And we have seen that Monte Carlo method will converge to one such answer, and the TD method will converge roughly to the value given by this estimated MPP, right? And then we also looked at what is called TD, n-step TD, where instead of looking at one step and then instead of just looking at one sample of reward and then using the V old estimate, so you just look at RT plus 1 and RT plus 2, and for the remaining return, you use your old estimate, which is this RT plus 1 plus RT plus 2 plus gamma square times V old of ST plus 2. So then we were thinking of what is a good value of n to use. And then we have seen that there is a method called TD lambda, which uses all possible n's and takes average across all of them. So it uses these weights, 1 minus lambda, lambda, like it uses these weights and takes a weighted average of all the n-step TDs, right? So if you just use that estimate, then you call it a TD lambda. And so this is roughly what we have discussed in our last lecture. So let's, in today's lecture, what we'll do is, now we understood how to estimate the value of a given policy, even in the model free setting, right? Even when we do not know the dynamics of the MDP, we know we can use methods like Monte Carlo to estimate V pi or TD or TD lambda. We can use these methods. Now, if you want to understand what is the optimal policy, how can we do that in the model free setting? That's what we'll look at in today's lecture. So we look at, as I said, finding V pi for a given pi is called the prediction problem, and finding pi star is called what? What did I say? It's called control problem, right? So we look at how to control methods, how to do control when we do not have the model dynamics. Okay. So we look at what is called model free control methods. So specifically, we look at again we look at two kinds of methods here. One is Monte Carlo based control and TD based control. So in TD based control, there are two methods which are popular, which is called SARSA and Q learning. If you looked at assignment 2 part B, these are the two algorithms which are asked to code. Okay. So this is what we'll try to roughly look at in this lecture. So when we had the model, what was the algorithm that we used for finding pi star? So policy iteration is one such algorithm, right? So what is policy iteration roughly? What do we do in policy iteration? You start with some arbitrary policy pi naught. You find v pi naught, which we call as policy evaluation, and then we do what is called policy improvement, and then get pi one. So what is policy improvement? We find pi 1 of s equal to argmax over a. So from v pi naught, we have to do this, right? From v pi naught, what we have to do? Which is q pi naught of s comma a, which is what? In terms of q pi, v pi naught, rsa plus into p pi naught ss dash into what else? V pi naught of s dash, right? So this is like we were doing policy evaluation first and finding V pi naught. And after that, we are finding pi 1 using this equation, right? We know already V pi naught from the policy evaluation. And then we just substitute this, we use this equation to get the pi 1, right? So now in the model free setting, do we know how are we doing policy evaluation in the model based method, like in the case when we have the MDP dynamics? Like this is how we are doing policy improvement. How are we doing policy evaluation? So you are iteratively using the Bellman expectation equation, right? So what is the issue of using that now in the model free setting? There we need the knowledge of P pi, SS dash, etc., which we do not know. But do we know any other way of doing policy evaluation now? That's what we revised, no? Just now. What did we do? Given pi naught, we want an estimate of V pi naught. We learned, right? Monte Carlo, TD lambda. So we know how to replace policy evaluation now in this algorithm, right? So are we done? Then is there any problem in implementing policy iteration algorithm if we just replace this policy evaluation with, let's say, TD algorithm, one step TD, let's say, I'll get an estimate of V pi naught. So can I use policy iteration now, or is there still some issue? Uh, no, anyway, we are not right now worried about convergence guarantees, but can you implement this first of all? Right? So what is like policy evaluation is taken care. We'll use TD lambda or TD or MC. We'll use something. So what is the issue still left in policy improvement? Is there any issue? To implement this, we need this, right? Which we do not know. Correct? So if we know these things, then we know how to improve the policy from V pi naught. If we do not know these things, we don't know how to improve, right? So then what is the solution? No, that's an expected reward for taking action A in status. We don't know the distributions. Huh? No, that is just one sample, right? RT plus one. If you are in status, if you take action A, you get one sample of that reward. So that will be RT plus one. Like it's just one sample from RSA. RSA is an expectation, right? Yeah, you have to use the samples in some way. So while teaching policy iteration, I mentioned one important point regarding model. When you don't know the dynamics, when you know the dynamics, there is some difference, right? Between these two equations. Like this is one equation, this is another equation, right? So do you recollect any such thing which I mentioned when I was discussing policy iteration? The difference between using equation one and equation two. If you use equation one, can you do in model free setting? Can you use equation one in model free setting? Why? Because that does not require model dynamics. You don't need RSA or you don't need P pi naught SS dash. So the simple change we'll do is instead of estimating V pi naught in the policy evaluation phase, instead of estimating V pi naught, what can we do? Estimate Q pi naught of S comma A, and then policy improvement will go through. Like you can happily use this equation, which does not require any knowledge of the MDP dynamics. Okay. So now we look at how can we estimate Q pi naught for a given pi naught. For a given pi, how to find Q pi using in the model free setting. Okay. If you know that, then policy improvement is trivial for us. Because if you have Q pi naught here, if you can estimate Q pi naught, then you can simply use equation one, which does not require any model dynamics. Okay. So let's try to understand how to So I've been using small q and capital Q interchangeably. Don't get confused, both the same. Okay. For the Q value, I mean not been consistent with the notation. Small q and capital Q both makes the same for us. Okay. Estimating q pi in model free setting. Okay, that's what we look at now. Okay. So let's say you want to use a Monte Carlo method for estimating q pi. Oh, what can you do? So let's say you want an estimate of q pi of s comma a. Can we use Monte Carlo method? Do you remember what is Monte Carlo method? So can we estimate q pi of s comma a using Monte Carlo method? How? Can anyone tell me? It's a straightforward thing, right? What is q pi of s comma a? Expected return given st equal to s and at equal to a. So previously we were just starting with state s and acting according to pi. Now you just start from state s, take the first action as a, and then from next state you follow policy pi. You continue the episode and keep following policy pi, and you continue the episode till you reach a terminal state. Then you get one sample of this expectation, right? So you just start, you take your s naught equal to s and take a naught equal to a, and you continue the episode. Like the environment will give you some reward and a new state, and then from a1 you act according to pi. Okay, the first action a naught alone you take to be equal to a, and after that you keep following policy pi. So whenever you have to take an action, you take according to policy pi, and you continue that episode till the end. So then you get one return, right, for this whole episode. So that return will be a sample for your q pi of s comma a, right? So then if you start multiple episodes, like you do this multiple times, every time you start, you take s naught equal to s and a naught equal to a, you get one sample of q pi of s comma a. So you do this multiple times, then you get take the average of those returns, then you get an estimate of q pi of s comma a. So, but one small practical issue that we'll face in this approach is, previously when you wanted an estimate of v pi of s, let's say v pi of s, if your initial state is s, and let's say some other state you encounter, some other state s dash later. So this episode is not just giving you one estimate of v pi of s. It is here, from here, if you look at from this point, you get one estimate of v pi of s dash also, right? Like you look at all the states that you visit. From that state, if you look at the remaining return, you get one estimate of v pi of that particular state. So every episode is giving you a lot of information here, right? Here, for example, if you use Monte Carlo every visit, you will get lot more samples, right? But here what we'll get is, like, if you are starting with s comma a, your first pair is s comma a, but after that you'll keep acting according to pi, right? So when, even though you visit state s again, even though you visit state s again, you won't take the action according to, you won't take action a, right? Like, let's say s2 is equal to s again, like due to some reason you came to the same state again, the environment has put you in the same state again. What will a2 be equal to? Will a2 be equal to a? It will be pi of s. So that means you won't get another sample of q pi of s comma a, right? If you want one more sample of q pi of s comma a, you have to take action a here, right? You have to take action a here. But if you take action a there, what will happen? Like, the return from here will not be q pi of s comma a. Because what is q pi of s comma a? You just take action A now, and for the remaining time, you act according to pi. If you want one more sample of s comma a and you just play action A some other time, then that means you are deviating from policy pi, right? Here you are deviating from policy pi. So the return starting from here won't be equal to q pi of s comma a, won't be an estimate of q pi of s comma a. You understand this point? So the initial, you are getting one sample only for s comma a, because whenever you visit s again, you are not acting according to a, you are acting according to pi. If you try to act according to a, you won't get any sample at all, because the first the return from the starting point won't be equal to q pi of s comma a, because for the rest of the time you are not playing according to pi. So this is a problem which you will face. So for every sample, like if you want one sample of q pi of s comma a, you have to start from that state. The remaining part of the episode will not contribute to samples of q pi of s comma a. So if there are a lot of actions, you have to start with s comma a for every pair s comma a to get a sample of q pi of s comma a. So if there are, let's say, n cross k or whatever, like if there are n states and k actions, so you have n cross k pairs, like nk pairs. So for each s comma a pair, you have to have multiple uh, samples, right? So this is an practical issue which you will face. But if the action and state space and action size is less, you can technically do this. So this algorithm, this plain version of Monte Carlo method, where you start from s comma a multiple times, is called exploratory Monte Carlo method. Exploratory start Monte Carlo method, because you are exploring all s comma a's in the beginning. Because you want samples for every s comma a, right? You want q pi of s comma a for every s and a. Then only you know q pi. So you have to start with every possible s comma a multiple times. So this is called exploratory start based Monte Carlo method, where you explore all possible S comma A pairs in the beginning. Okay. But if the state space and the action space is large, then it's not very practical. Okay. So, so can you think of any solution for this? Right here, what is happening is when we try to act according to policy pi, we are not getting S comma A pair again. Right? If you started with S comma A, and if you act according to pi, you won't get S comma A again. Like, let's say if pi of S is not equal to A, you'll never see S comma A pair again in that episode. But if you want to if you want to see S comma A pair again and again with a good chance, what can we do? Or when will this be true? Like, even though you are acting according to policy pi, you might again see S comma A pair. If policy pi, previously we were looking at only deterministic policies, right? What is this policy pi one? It's a deterministic policy, right? Because when we do the policy improvement here, we are getting a deterministic policy. Pi one is a deterministic policy, right? Because for every state you are fixing one particular action. So that means if pi of s is not equal to a, you will never see that pair if you play according to pi. But what if our policy is not a deterministic policy? What if our policy is a stochastic policy? Right? If your policy is a stochastic policy, which will say play A1, if you are in state S, act according to A1 with probability half, act according to A2 with probability half, or like there is some distribution among the actions. It's a stochastic policy, let's say. Then there is some chance of seeing the same pair again, right? If pi itself is a stochastic policy, then although you play according to pi, at some point you might see the same state action pair. When you reach state S, again, because it's a stochastic policy, you'll throw a coin toss according to the probability distribution of that policy, and you'll decide the action. So there is some chance that you again see the same state action pair S comma A. So to solve this problem of very less samples for S comma A, you can make your policy stochastic. That is one option. But what happens to our policy improvement guarantee? Like our policy improvement is giving a deterministic policy for us, right? We know that this equation one will definitely improve our policy. Like you have pi naught, you estimated q pi naught. Then if you improve your policy according to equation one, you are guaranteed that pi one or v pi one is greater than or equal to v pi naught. That is policy improvement is guaranteed if you act according, if you improve your policy according to equation one. But if you make your policy a stochastic policy, let's say instead of making this greedy, like this is like a greedy behavior, right? Pi one is like you are greedily improving pi naught using the q function. First of all, our estimates are not very accurate right now because we are in the model free setting. We are we are not solving using the matrix inversion or Bellman expectation equation. So we are roughly estimating v pi naught using some Monte Carlo estimates, etc. So we are not very sure about our estimates. First of all, that is one motivation to have some randomness in your update. You don't want to be greedy. Like maybe you have to be epsilon greedy. Like in the bandit setting, we have seen this, right? Because we have only mu bar of A, mu t bar of A. We don't have mu of A. Like we don't know true means. We only know the sample averages in our bandit setting. So because our sample estimates could be wrong with some probability, we wanted to behave epsilon greedy instead of greedy. Similarly, that is one motivation to go to epsilon greedy improvement instead of greedy improvement. So what will be epsilon greedy improvement intuitively? Your new policy pi 1 will be with 1 minus epsilon probability, you act according to this action. Okay, you act according to the action given by this equation. When you are in state S, with 1 minus epsilon probability, you behave according to the action given by equation 1. And with epsilon probability, what will we do? Take any action at random. Okay, if you are in state S, with probability 1 minus epsilon, you act according to the action given by equation 1. And with 1 minus like with epsilon probability, you take any action at random. So that's called an epsilon greedy improvement policy. Okay. So you act greedily with probability 1 minus epsilon and you behave randomly with probability epsilon. Let's say if there are 3 actions and this equation will give you action A1 for state S. You take action A1 with probability, let's say 0.9, and with probability 0.1, you take any of the actions A1, A2, A3 randomly. Okay. So that will be our new policy. No, if you in this thing, if you play action A with probability, let's say epsilon, then the first sample will not be a estimate of q pi of s comma A, right? I did not understand. Yeah. No, we are changing our policy itself, right? Here. Previously, we had a deterministic policy. So you want to estimate the v pi or q pi of whatever policy you have, right? So if you want to estimate a deterministic policy, you have to play a deterministic policy. Like you have to interact using the same policy, right? If you want to estimate pi, you have to interact using pi. So if you are estimating a deterministic policy, your interactions will be deterministic. Unless you make your policy of interest itself as a random policy, you won't get randomness in the behavior, right? Is it clear? Because if pi is a deterministic policy, if you act randomly, then you are not following pi. But if your pi itself is a random policy, you are not behaving as randomly as you want. You are only behaving according to pi even in the new setting. But it turns out that your pi itself is stochastic. So even though you behave according to pi, you'll still have some chance of seeing s comma A because the pi itself is stochastic. If pi tells you to take action A with probability point, let's say point 1, you will take action A only with point 1. You won't take action A with point 2. You are not taking some arbitrary random policies. You have a random policy, you are playing according to that random policy. With 1 minus epsilon, you are playing this action. The action given by equation A. Like you would have had estimates of q pi of s comma A, right? So you substitute that equation and find pi 1 of s. Like you don't call it pi 1 of s, you just call it something, right? You call it, let's say, A star or something. You just call it A star. So with probability 1 minus epsilon, you behave according to A star. With probability epsilon, you behave random. Okay? Is this clear? Before I proceed further, at least is the definition of pi 1 clear? You have some policy pi naught. You estimate q pi naught. Then your policy pi 1 will be, so pi 1 will be a stochastic policy, which says pi 1 of, maybe I'll write it down. So you have pi naught, you did policy evaluation, and you got q pi naught of, you got q pi naught. Now you're, instead of doing strict policy improvement, you are doing epsilon greedy policy improvement. So what is epsilon greedy policy improvement? So your pi 1 will be a stochastic policy, which tells you the following: pi of A given S is equal to argmax over, with equal to 1 minus epsilon for A equal to argmax over B q pi naught of S comma B, okay, and equal to epsilon by mod A for A not equal to this, okay. Maybe here you'll have one more this thing, because in that random action you could also play this action, right? With 1 minus epsilon probability you are playing this action. With the remaining epsilon you are playing any action at random. So every action has a probability of epsilon by mod action set. So this is the exploratory part for this, okay. So this is what I mean by epsilon greedy policy improvement. Is this clear? So previously, if you take epsilon equal to 0, we'll get back our previous thing. If you take epsilon equal to 0, what will we get? You play that particular action with probability 1, where A is argmax over q pi of S comma A, right? Any doubts at this point? Is everyone clear about the definition of pi 1? No, that's a hyperparameter, which, yeah, so you have to, like, there are some epsilons which are standard, but for example, in the policy, in the epsilon BT algorithm of bandits, we have done some theory, right? It says that if epsilon is like t power 2 by 3, like 1 by t power 2 by 3 or something, then we are guaranteed to have t power 2 by 3, like, etc. So here we are not going to do those calculations. We are just giving you some intuitive techniques to understand how to overcome those problems. Okay. So to do such a detailed analysis, you require heavy mathematics for this part. Okay. But at least the definition is clear, right? And the motivation is also clear, right? Because now we have an stochastic policy. So now if you want to estimate q pi 1 of S comma A, what will we do? We'll start with state S comma A, and you, after that you behave according to what? Policy pi 1. So although A is not equal to this particular A, with some probability you are playing other actions also. So there is some with there is at least this much probability that you'll see the same, it's the same A again whenever you are in status. Whenever you're in status, there is some probability of seeing action A according to your policy. So that will give you few more estimates for q pi of s comma n. Okay. So now, what is the question that we want? Improvement. No, I did not understand the question. Yeah. So this is the policy improvement part. Like you are looking at all possible B's and then looking at what is the best Q of Q pi naught of S comma B. This is the same thing which we had before. Previously, we were improving in a deterministic way, which says that whenever you come to status, you play this particular action. Now we are saying play this action with probability 1 minus epsilon, play other actions also with probability epsilon. Because if you make it deterministic and say you always play action A, you won't get this exploration behavior in the evaluation phase. Okay, so this is a trick which we are playing, and now the question is, now you had some policy pi naught, right? Now previously we know that if you do policy improvement, we had this guarantee that v pi 1 is greater than or equal to v pi naught. Okay, now we are not behaving greedily, right? Now we are doing epsilon greedy behavior. Are we still guaranteed that our new, let's say this is pi 1 is a stochastic policy, which is an epsilon greedy improvement over pi naught. Now I'll estimate q pi 1, and after that I'll find pi 2 again in this epsilon greedy improvement way, right? So am I guaranteed that v pi 2 or v pi k plus 1 is greater than or equal to v pi k, right? Previously, we proved that for deterministic policies, in the case of deterministic policies, since we are strictly improving, like we are taking argmax over that, we were able to show that we'll always have this guarantee. Now the question arises whether such a guarantee is possible in the epsilon greedy improvement as well. Like pi 1 is a stochastic policy. Now you estimated q pi 1, and after that you find pi 2 using this epsilon greedy improvement. Now whether v pi 2 is strictly or at least as good as v pi 1. So it turns out that this is also true. Okay, if I have an epsilon, as long as pi 1 is also epsilon greedy, then with the same epsilon, pi 2 will also be, if you keep the same epsilon, because all this if pi 1 is an epsilon greedy policy, right? Again you estimate q pi 1, then you find pi 2. Pi 2 is also an epsilon greedy policy. As long as you maintain the same epsilon, for the given epsilon, v pi 2 is, if you improve using epsilon greedy policy, then we can guarantee that v pi 2 is greater than or equal to v pi 1. Okay. No, that we cannot write. If you start with some policy which explores at least with probability epsilon, then we can write. So we are not telling, no, you don't start with a deterministic policy. Maybe you can start with an epsilon. Yeah. So the minimum requirement here is, if you want an improvement, like this policy, whichever you are, the previous policy should also have some exploration component in that. Because all the sequence of policies that we get will explore with probability epsilon, right? That's how we defined our policy improvement. So pi 1 is an epsilon greedy policy. Then you estimate q pi 1. Then pi 2 will be again an epsilon greedy policy, right? Because you are again doing epsilon greedy improvement. So as long as the policy which you are considering explores with probability at least epsilon, that is every action should have at least this much probability. Like pi of A given S for any action should be at least this much. That means with at least probability epsilon, epsilon by k, let's say k actions are there, every action has at least epsilon by k probability of improving, like playing. Then we call it an policy which explores at least with probability epsilon. Okay, so these are also called epsilon soft policies. Epsilon soft policies means at least with probability epsilon by k, every action should have at least probability epsilon by k, where k is a number of actions. K is the number of actions. Is this clear? The notion of epsilon soft is clear? Yeah. Yeah, you can start with any epsilon soft policy and then no, the end will also be another epsilon soft policy. So what will converge to is the best policy among epsilon soft policies. So if you will converge to a policy which is the best policy among epsilon soft policies. So you look at all the policies which will explore at least with probability epsilon. Like collect the set of all policies which will explore with at least probability epsilon. Among all those policies, you will converge to the best policy. Is this clear? Because we'll always be in the epsilons of policies, right? Because we are only doing epsilon greedy improvement. Maybe if you decrease epsilon, let's say as a function of time, slowly, then maybe you will converge to the greedy, like the optimal policy. Maybe the epsilon greedy improvement will hold as long as the new epsilon is less than the old epsilon. Okay. So roughly, this is what we are telling. So if you do epsilon greedy improvement, we'll still have this policy improvement theorem. The policy improvement theorem will still hold. The only condition is we'll converge to the only thing is we'll converge to the optimal policy among epsilons of policies. If the optimal policy is a deterministic policy, then we won't converge to that because we are only searching among epsilons of policy. So we will be off by the optimal policy by this much. Okay. So maybe I'll do the proof of this in the next class. I'll continue with the rest of the methods in this class. So this theorem, which is saying that if your policies are epsilon soft, your epsilon greedy improvement will strictly preserve this guarantee. Will preserve this guarantee that v pi k plus 1 is greater than or equal to v pi k. Okay, similar to the deterministic policies. Like if you do epsilon greedy improvement, we'll have this guarantee. That's what we are saying. Okay. So now we are fine, right? Now we know how to do control with in the model free setting, right? At least we know how to do it with Monte Carlo method, right? So what is the method? You start with some arbitrary, let's say epsilons of policy. You start pi naught is some arbitrary epsilons of policy. Epsilons of policy means you have to ensure that every action has at least this much probability. Okay. And with 1 minus epsilon, you can do whatever you want. Okay. For example, a random policy, uniformly random policy is epsilon soft, right? What is a uniformly random policy? Every action is taken with probability this, right? So that is an epsilon soft policy with epsilon 1, right? Because every action has at least this much probability. So maybe you can take pi naught to be some uniform random policy, which takes every action with probability, equal probability in every state. And then you evaluate q pi naught, like some epsilons of policy, some arbitrary epsilons of policy. So do you know did you understand the difference between epsilon soft and epsilon greedy? Now what is epsilon greedy? you have some policy given to us. You are taking some arbitrary action with probability epsilon by k, and with remaining probability you are taking this particular action. So epsilon soft policy is just telling that every action should have at least this much probability. So this is one epsilon soft policy. Like epsilon greedy is one epsilon soft policy, because every action has at least epsilon by a probability, right? Because what is the probability for any action? You have this, right? Any action has this probability, so that means it's an epsilon soft policy, right? Even this particular action has this probability. Epsilon soft is just telling that every action should have at least epsilon by k probability. What do you do in the 1 minus epsilon part is up to you. If you do that 1 minus epsilon in the greedy way, that is called epsilon greedy policy. If you do that 1 minus epsilon also in the exploration, then it's like uniform policy, right? You just sample any action with probability 1 by a. This is also an epsilon soft policy. It's just that you are fully exploring here. Anyway, you need not worry too much about that, but I just want you to appreciate that these two are slightly different. But epsilon greedy is an epsilon soft policy. Okay. So you start with some arbitrary epsilon soft policy, and then you do policy evaluation using, let's say, Monte Carlo method, and you estimate q pi naught. Then you do epsilon greedy policy improvement. Then you get pi 1, then you keep doing that. Okay. Then you will converge to some policy which is the best policy among epsilons of policies. No, like here, this is epsilon soft for any epsilon, right? No, even if a completely random policy is epsilon soft for any epsilon, right? It is epsilon soft for 0.1 also, it is epsilon soft for 0.01 also. You have to set one epsilon for your whole problem, and pi naught should be epsilon soft. So set pi naught should also be epsilon soft. Yeah, because we are choosing like that, right? This is how we are choosing. Pi 1 is an epsilon soft policy, right? Because we are playing every action with probability at least epsilon by k. Okay. Yeah. So if pi 1 is let's say epsilon 2 greedy, like pi 1 is epsilon 1 greedy, let's say. If epsilon 1 is less than epsilon naught, then we're fine. I think the policy improvement will still hold. Okay. But anyway, right now you can just think of constant epsilon, some small epsilon, maybe you can think of some small epsilon. Okay. So now the Monte Carlo method is clear, right? So you just do this and you keep improving your policy using epsilon greedy policy instead of greedy policy improvement. So this what generally what people do is to estimate q pi naught. What we have to do, we have to have multiple episodes, right? You have to collect multiple episodes of data and then take the average over the returns to get an estimate of q pi naught, right? If you want an estimate of q pi of s comma a, you have to have multiple episodes or multiple samples of q pi of s comma a and then take average of all of them. So generally in practice, what is done is you just do one episode of interaction and see whatever s comma a pairs you encounter in that. So you just do one episode of interaction. Some s comma a pairs you will encounter, right? In that, you just update q pi of s comma a of all those pairs whichever you see in that episode, right? You just do one episode of interaction. In that episode of interaction, some s comma pairs will come. So for every S comma pair that you encounter, you will have a sample written. So you just update your q pi of S comma A for those pairs. Then after that, you just do epsilon greedy improvement. So after every episode, you will do the epsilon greedy improvement. You won't fully estimate q pi naught. Similar to what we did in the value iteration, right? You remember what we did in the value iteration? We did not estimate v pi naught fully, right? We just estimated v pi naught by doing one Bellman expectation iteration, and after that we simply improved our policy. So this is called generalized policy iteration, where you don't fully estimate your v pi naught or q pi naught. You approximately estimate your v pi naught or q pi naught, and then you just improve the policy. So if you do approximate policy evaluation, that's called generalized policy iteration. If you do the full policy evaluation, then it's called policy iteration. Generalized policy iteration refers to approximately estimating v pi naught or q pi naught, and then you immediately improve your policy. And then again, you estimate approximately v pi 1, then again you improve. Okay. No, you just start with some arbitrary S comma A and then run one episode. So in that episode, a lot of S comma A pairs might come, right? Every state action pair, every step you'll get some S comma A, right? You just update for all those S comma A pairs. No, even if you take according to the policy, if you see the pair S comma A, that means the action is A, right? So you started with the status, like you encounter status and you took action A. So that will be a sample of q pi of S comma A, right? Why you took that action is because you behaved according to pi, but that doesn't matter for us, right? You are in status and you took action A. That's all matters for us. Like if you want a sample of q pi of S comma A, your ST should be equal to S and AT should be equal to A. Why you choose AT equal to A does not matter. Whether you behaved according to pi 1, that's why you choose AT equal to A, or whether you behaved according to pi 2 and you choose AT equal to A, that doesn't matter. All that you need is condition on ST equal to S and AT equal to A. So whatever policy you follow, if you see a pair S comma A, ST equal to S and AT equal to A, the remaining return will give you an estimate of Q of S comma A. No, all S comma pairs might not occur in that particular episode. So there will be some mistakes, like there will be some mistakes. But in the next update, maybe you'll improve that policy. So the same with Bellman like value iteration, right? You are just doing one iteration of Bellman expectation. Huh? No, for example, if you do Bellman expectation, like if you do value iteration with, let's say, the asynchronous method, right? So this is just, we're just saying approximately we're estimating Q pi naught and then we are improving. So we can argue that this method will converge to pi star if epsilon, like at least epsilon among the epsilons of policies. Okay. So as I said, this is called generalized policy iteration, where you are not fully estimating Q pi naught before you improving. Because there is no notion of fully estimating Q pi naught, right? Because even after thousands of episodes, you can only say that it is an approximate value of Q pi naught, right? Because this is like an average. So if you, unless you have too many samples episodes, you cannot come up with some concentration inequalities like UCB. Like you have to use very some other sophisticated concentration inequalities to argue such things. Because previously we had only one random variable. Like in the bandits case, we use Hopding inequality to say that if you have n samples, you can say that the true mean will be within epsilon of the sample mean. Now you have to have more sophisticated concentration inequalities because you need some this is some this is some MDP, there is some Markov property. You have to use some other techniques to bound how far your Q pi naught, sample Q pi naught will be from the true Q pi naught. Okay. So if you want, like, there is a book in the references which I have uploaded in the FCH. There is a book called RL Theory book by some authors. So they do all these things very rigorously. They talk about an MDP and they talk about if you do couple of episodes of MDP and estimate Q pi naught, whether the average that you get, average returns that you get, which is an estimate of Q pi naught, how far will it be from the true Q pi naught? So here we are not going to do all those analysis, but uh, we are just giving you some ideas on how to solve for optimal policy in the model free setting without proving any rigorous guarantees. True Q pi naught is the true reward estimate expected. Yeah. No, then the same definition which we are using, right? What is a true expected reward of an arm? That's in that sense. This is what I was calling as mu of a. I was calling as the true mean of that reward, right? Similarly, here mu of a is like expected RT given AT equal to A, right? In our arm setting, bandit setting. Similarly, here this is what I was calling as true mean, right? Similarly, true Q means the actual Q definition, which we are calling Q pi of S comma A will be expected GT given ST equal to S, AT equal to A. This expected value is what I'm calling as a true Q pi. But here we are in the Monte Carlo, we are just estimating it, right? By running multiple episodes and looking at the GTs and taking average of all those GTs, sample average of all those GTs. That's the estimated Q pi. This is the true Q pi is what I'm. Okay. So till here everyone is fine. How to do control with Monte Carlo? So you just move to epsilon greedy policies and then uh, you do the regular Monte Carlo and you are just updating after you are doing improvement after every episode. Okay, those are the only things that are different. Okay, now this is about using Monte Carlo for control. Then what is the topic that we want now? How to do control with TD methods, temporal difference methods. Okay. So similarly, we'll also look at only similarly we'll look at epsilon greedy improvements. So the rest of the thing will remain the same, except that here in this part, uh, just this part will change. Okay, instead of this part will be the same. We'll do epsilon greedy improvements instead of estimating Q pi naught using Monte Carlo. We'll just estimate Q pi naught using TD method. Okay, that's the only change we'll do. So now I have to just explain you how to do uh, uh, TD based estimation for what? Q pi. TD for Q pi, right? If you know how to estimate Q pi using TD, then you know how to do control also. You just substitute that in this algorithm. Okay. So this you already know, right? You know how to do TD algorithm for what? V pi. Now we have to just see how to do for Q pi. Sorry. So how did we do? How did we derive TD algorithm for V pi? Do you remember how we found the TD update for V pi? We just looked at the Bellman expectation equation and then did a sample version of that, right? So what is Bellman expectation for V pi of S? R pi S plus gamma times sigma S dash. Um, V pi S dash P S S pi, right? So here We had a general update rule, right? What was the generic update rule we had for any algorithm for estimation? We knew of S, we knew of ST equal to V old of ST plus some small constant times our new estimate minus old estimate, right? This is a general generic update equation we had, right? In this, we just got inspired from this equation and substituted something, right? So the first part is what if you act according to pi in status, what is the expected reward you get? So RT plus 1 is one sample of that expectation, right? Because you are in some status and you are acting according to policy pi, right? No, so RT plus 1 will give you one sample for this. Then plus gamma times, and there are a lot of S dashes which are possible, but the environment will give you one particular S dash, right? Because you are in status and you interacted according to policy pi. So you are in status and you interacted according to policy pi. Then there are a lot of S dashes possible. The environment will sample one S dash and give you ST plus 1. So instead of taking an expectation over all S dashes, we'll just use ST plus 1 because that is one sample of all these S dashes. So in that, what we'll do, we substitute V old of ST plus 1, correct? So this is how we did TD for V pi. So TD for Q pi will also be very similar. You just write Q pi of S comma A using Bellman equations, which we know. Like you just use the definition of Q pi of S comma A and write in as if you know the model dynamics. You'll get some expression. Then you just take samples from that expression. Okay. So let's try to write that. What will be Q pi of S comma A? Can you write Q pi of S comma A again in terms of Q pi of S comma A? Like maybe some S dash A dash. So what is the definition of Q pi of S comma A? First maybe we'll write in V pi, then we'll write again that V pi into Q pi. Okay. Which is equal to RSA plus gamma times sigma S dash. What else? V pi of S dash into P A S S dash. Correct? Now we want again Q pi only, right? Because we want everything here, we new, we old, right? We want everything in like here we want Q new and Q old kind of thing. Okay. So again, let's convert this V pi also into Q pi. Okay. So what will we get? RSA plus gamma times sigma S dash into P S S dash A into this V pi, we'll just write it in terms of Q pi. Okay. What will that be equal to? What is V pi in terms of Q pi? So you are acting according to policy pi. So what is the problem? Like you will get Q pi of S dash comma A, but A is sampled according to policy pi. So you'll get, you have to multiply this with A given S dash sum over all A, right? So I just substituted the definition of V pi, right? V pi is a what? You just act according to policy pi. That's what I wrote. You with probability A given S dash, pi of A given S dash, you take action A. If you take action A, this is the return that you'll get Q pi of S dash comma A. Maybe I'll use A dash here because A we are already using here in the first term. Okay. So sum over all A dash. Okay. So this is what RSA plus gamma times sigma S dash PSS dash A sigma A dash pi over A dash given S dash into Q pi of S dash A dash. Okay. So now we'll first write the generic template for our update rule. What is our generic template? Q new of STAT equal to Q old of STAT plus what is that after that? Some small constant times our new estimate minus our old estimate of STAT. Right? This is our generic template, right? In this, what we'll do, we'll just get inspired from this equation and write some sample, some estimated version of that. Correct? So what can I write for this? For this term, if you are in some state S and act according to action A, which you did, ST is equal to S and AT equal to A, then what is RT plus 1 will be an estimate of RSA. So here we can just write RT plus 1 plus maybe gamma times. Then this is just two expectations, right? This is sum over all possible S dashes, and this is sum over all possible A dashes. So there are a lot of S dashes which are possible, but the environment will sample one particular S dash for us, which is ST plus 1. And after that, so the environment will give you ST plus 1. After that, how will you behave? You will behave according to policy pi. So you just right now you are in some state ST, you acted according to AT, you got a reward RT plus 1. Then the environment will also give you ST plus 1. Then AT plus 1 will be sampled according to policy pi. Pi you know, right? Because that is what you are estimating. So you just take the state given by the environment, which is ST plus 1, and then sample action AT plus 1 based on ST plus 1. Pi of A given ST plus 1. You just sample one AT plus 1 like that. So based on that, what will you get? You just substitute Q old of ST plus 1 and AT plus 1, where ST plus 1 is the action given, is the state given by the environment, and AT plus 1 is the action sampled according to pi for the state ST plus 1, right? Because AT plus 1 will be based on ST plus 1, right? So the environment will give you state ST plus 1, and then you will use your policy pi to sample AT plus 1. So that's all. This is the update rule for TD method for estimating Q pi. So this algorithm is referred to as SARSA. This is because we are using ST, AT, RT plus 1, ST plus 1 and AT plus 1, all these samples to do this update. Okay. So this is why it is called as SARSA. Okay. State action, reward state action. Okay. So we are using all these 5 samples to do this update rule, to do this update. So now you know how to do control with TD. What you'll do is you'll start with some arbitrary soft policy like epsilon soft policy, or you can take it uniformly random policy if you want. You just start with some random policy, and then you estimate that policy using this update rule, and then you epsilon greedily improve that and get new policy. So one more interesting thing is here in the Monte Carlo control method, when when are we updating our policy? When are we improving our policy? After every one episode, right? You start with some policy, you run one episode, then you whatever S comma A pairs you see, you just do the update for them, and then you epsilon greedily improve that policy. So in this SARSA method, what you'll do is You'll start with some arbitrary policy. Then you will do this. After every interaction with the environment, you will update your policy. You won't even run one full episode. Okay. Like you'll do it in an online fashion. So after every one update of this SARSA equation, you greedily improve your epsilon greedily improve your policy. Okay. So right now you have some policy, you act according to that policy, then you get RT plus one, ST plus one, then you choose your new action as the improved action. Like you take your next action as a uh, like you just calculate your improved pi after every step of this update. You don't wait for one episode or anything. Because in the Monte Carlo, you won't even get one update, right? For one update, you have to wait for whole episode. Because what is the update rule in Monte Carlo? You want GTs, right, for update. So the GT you'll get only after one episode. Here to update this, you only need RT plus one and ST plus one. So after every one action, you are able to update your Q function, right? So you are estimating your Q function. After every action with the environment, you can update your Q function, at least for that pair, S comma A. So after that, based on that new Q, you improve greedily, epsilon greedily, and then take the next action according to your new pi. So it's the same thing. Like as I said, we cannot run this policy evaluation infinitely, right? You have to decide after how much time of policy evaluation you want to do the improvement. So in Monte Carlo, we do it after every episode. In the SARSA algorithm, uh, we do it after every interaction with the environment, after every action. Okay. And Q learning is a slightly different version of SARSA. So what I want to do is maybe I want to take an extra class since I lost one class in the last Monday. I'll take one extra class and cover the Q learning algorithm. So maybe tomorrow or day after tomorrow. Day after tomorrow is a holiday, is it? You want tomorrow? Okay, so maybe I'll take it tomorrow sometime in the late evening and I'll record it anyway. So if you miss, one of you miss, that's okay. You can watch the recording. Yeah. Okay. Thanks. I'll announce the timing. Okay. Yeah, tomorrow in the extra class, I won't take the attendance. Okay.